All right, getting it rolling here with equilibrium. So I couldn't find a video of the paper wall fight equilibrium, which we would have done in class, but we can't throw paper back and forth, unfortunately. Can't be picking up something that someone just touched in these kind of times. But it does work. I'll mention about what that is later. But I can show you this other demo here. It's not as exciting as throwing paper at your classmates, but it does kind of maybe show you maybe the idea of equilibrium. So let me just show you this. This is a video on YouTube here. I've got the sound muted because you don't really need to hear liquid water being poured back and forth. But what this guy has, he's just got like some green food coloring and water in the beaker on the left. And he's got no water at all right now in the beaker on the right. And he's going to show you what he's using. Okay, so in his hand on the left, he's got a 250 ml beaker. And he's got a 100 ml beaker on the right, okay? And so he's just going to dunk those in as much water as he can and fill up as high as they go and just pass water back and forth. And so I think eventually he speeds this up. I might pause and fast forward here in just a little bit. Of course, the first time, the little one can't do anything, so you fill the little one up as full as it can go, pour it back. Okay, this one can get completely full, so it gets poured over. And now the little one, he puts it down. Looks like it can almost fill all the way to the top. And he just keeps doing this. I mean, hopefully you can kind of get the idea. He just fills them as full as they can go. And you can kind of see the water starting to build up there on the right. So in the beginning, this thing is not at what's called equilibrium. So now it's going into fast time. He keeps doing it back and forth, back and forth, back and forth. But hopefully you can kind of see what's happening here now. Take a look at where the liquid water levels are. So like the one on the left, right, it's at about the 1600 mark and then it's down. Now it's at that 1600 mark and then it goes back. It's not really changing with time. It almost looks like it's not, okay? So when you get to this point, it wasn't doing this in the very beginning, but it is now. Now we say the thing is at equilibrium. And so a key thing that happens at equilibrium is how much water he's pouring from the right to the left now is equal to the amount of water he's pouring from the left to the right. So look, he's going to show you that, okay, the amount of water that the 250 is taking up is the same amount as that beaker on the right full. When he was pouring it back and forth, he was just ended up eventually passing the exact same amount of water back and forth. He kept doing it. It looked like overall nothing was changing, but it was still moving even though the net changed. The net change was 0. It looked like it was the same because the rates were the same. He was pouring the same amount of water to the left as he was back to the right. So that is a state of equilibrium. He wasn't there initially, but he eventually got there. And so what we could have done with paper balls is we usually split the class in half, and there's maybe like 15 people on the right side and 8 people on the left half, and you just start throwing paper back and forth, and we'll say stop, and then we'll count and see how much paper is on each side. And then you start up again, you keep doing it, it'll hit equilibrium. You keep stopping, you'll get the same amount on each side. It's kind of amazing that it works, but hey, equilibrium works. So here's the reality to all this. All the reactions, we've lied to you so far. We've always considered reactions only going one way. We've always counted that like it's the forward reaction, like this stuff right here. The reality is reactions can also go backwards, especially when you have a closed container. Okay, you need a closed system, meaning reactants can't get in or out, products can't get in or out. Then you've got a closed system, and then you get what's called equilibrium. Things are going back and forth. So it's not that reactions stop at equilibrium. It's just that they look like it. No net change. Okay, so the overall change is 0 at equilibrium, but they're still moving. They're still going back and forth, back and forth. The big technical term is dynamic equilibrium. So let me just let me see what I got here. Yeah, so here's some of the properties that you would see at equilibrium, right? We've got, let me highlight this here, we got no net change. That means, are things still going? Yeah. But if you were to measure like the molarity changes, you'd get no change. It would stay the same molarities. If you're measuring the pressures maybe in the flask, it wouldn't change because it would stay the same. Why is it equilibrium? Because this is key. The rate of the forward reaction is equal to the rate of reactions going in reverse. Okay, so keep in mind, they are still going, but it looks like, to your eye, it's going to look like nothing's happening. But they actually are. And the idea is that this only works in a closed system, so reactants can't get in or out. So we're thinking about maybe a closed system. Right now, this water bottle I have here is closed. The water inside can't get in or out. I would have a closed system. You can imagine what would happen now if I were to tip this over. It would be an open system. I don't want to make you think, though, that a lid off is necessarily an open system. If I've got reactants and products that are in the water in here and they're reacting in the water, they're not leaving. They're not going anywhere. So that could still be considered a closed system. So be careful. If the reactants and products can't leave, that's a closed system. That's when equilibrium happens. Just maybe another little image here that I want to show you with equilibrium. So if I start with maybe, let's do this. I think I can put like 100 molecules of A and none of B to start. And can we count? Yeah, so if you look in the upper corner up here, you can count how many of each particle are there. So we're definitely not at equilibrium because it's changing. Now this is a particulate level. We're seeing individual particles. So it's going to maybe not be exactly the same each time, but it's going to eventually come close to something like an equilibrium. And so at equilibrium, as soon as one of these goes from A to B, pretty much one of them goes from B to A. So if two of them go from A to B, then two B's turn into A's back and forth. And so they're kind of going back and forth, and this would simulate particles in a reaction. So I'm looking at the numbers of A and B right here, and they're roughly staying the same. I mean, it's fluctuating a little bit. These are particles. So it's going to do that on a big level, like in a beaker or something. There's billions upon billions of particles. So you wouldn't actually see the change here. So now it's finally hit, looks like it's finally hit equilibrium because it's not really changing now anymore. It's kind of roughly staying the same. All right, getting back to the meat of stuff here. Here we go. That's what equilibrium would be. So when you see a graph maybe like this, it's plotting reaction rates versus time. You see the forward reaction is going to be fast at first up in this region, and the reverse reaction is going to be slow at first in this region, but this one is quickly speeding up, and this one is quickly slowing down, and at some point they reach the exact same rate. That part right there, this right here, is when we have finally reached equilibrium. See if I can spell it. No, it's right there above me. Where we get that flat line, where the rates are exactly the same. The forward and reverse reaction rate are exactly the same at equilibrium. Here we go. Where are these graphs at equilibrium? Well, now this is a slightly different graph from the one up here. This one up here was graphing reaction rate versus time. This one's graphing, more commonly, concentration versus time, or molarity versus time. So if this is a closed system, I would say the equilibrium point would be right here. That's about where they're all level. Here, this one probably reached right there. So all of this would be equilibrium. I'm going to abbreviate EQ, and this one's EQ. And so, no net change with time. Those reactants and products aren't changing with time. It turns out, here's what the reaction that it's trying to show you. We're going to use reversible arrows. There you go. So, where they all sort of level off. The other thing to note about this is in a reversible reaction, if you look at the first graph here, this one right here, it looks like we're starting with all reactants and no products, like you would expect down here, all reactants and no products. But on the other one, we started with only products, no reactants. And it also can reach equilibrium from the reverse side. Isn't that amazing what equilibrium can do? Just so amazing, isn't it? All right, so that's kind of a little bit overview of equilibrium itself. Now you can take a look at these numbers. Probably isn't sticking, nothing's really sticking out to you, but they're all related. If you look in the tables, you might want to pause this and take a look and see what the heck, how can they be related? We've got a first set of conditions in the box right here. So if I start with 1 molar nitrogen and 1 molar hydrogen in a closed flask and no NH3, turns out it'll react, and this is what will happen. It'll eventually hit equilibrium such that these concentrations don't change. Here's the reaction right here. If instead I only start with NH3 in a closed container and none of these, I'll let it go to equilibrium. It turns out these are the concentrations at equilibrium. Again, where nothing's changing. No net change is happening. And then lastly, I could start with all three of them. And if I do that, these are the numbers I'm going to get. So, I don't know if you can pause this now and actually figure out how all these numbers are connected in each case. So they're connected in a certain way in this case. They're connected a certain way in that case. And they're connected a certain way in that case. I'm guessing you're not going to figure it out unless I tell you or you look it up. So here's what happens. It turns out when you take the equilibrium concentrations, if you square the number for NH3, Square that molarity at equilibrium. And then you divide it by the nitrogen equilibrium concentration. And then you divide it by the cube of the hydrogen concentration. You're going to get this value right here. You could do that with all these. You can square this one, divide it by nitrogen, divide it by this one cubed. You're going to get this value. Same thing with this one. But that didn't really stick out to you, did it? But it's actually not that complex. It took people a while to see this, I'm sure, but they eventually figured it out. And so here's what they're finding out. Now, we'll get to what these numbers mean a little bit more and how we can get to that right now. But it turns out here is some of the equilibrium expressions here. Now, I don't like the fact that I have KEQ here. I should really have KC. KC. And what that means is a capital K is the reaction constant. Okay, so let me move that over here and write that down. K is going to be equilibrium constant. And it's abbreviated with a K. Now, what the C means is that it's based off of concentrations. There are times when we might have something called KP. KP it's an equilibrium constant as well, only it's based off of pressures. You might have something called KSP. That's also an equilibrium, because it's got the capital K. The SP is little, like the C there. SP means something about solubility product stuff, which is, don't worry about that right now. You're going to see when we eventually move on, K with a capital, big K, normal there, but instead of a C, you see a little A. That means for like acids that are in equilibrium and stuff. So Ka is the acid constant. So whenever you see the big capital K, that's an equilibrium constant of some sort. Okay, so for any reaction, here's how you do it. You can try to take a look at this, right? So the coefficient of C, if this is your reaction, you pretty much have that reactance to the C power, this reactance to the D power. It's all divided by the reactance on the bottom. Let me show you what I mean. Let's go back to this one that was up top, right? So here's the reaction right here, right there. Okay, so I need to do what does K equal, right? What does K equal? And this is going to be Kc. We're going to base it off of molarities, right? Kc. This should have said Kc. That's the old way with the EQs. All right. Well, what's on my product side? It's NH3. And I'll put the molarity, so I'll put it in brackets. What's the coefficient in front? Oh, it's a 2. So, it's squared. That 2 goes up top. Now let's draw the denominator. What's on the bottom? Now, it doesn't matter which one I write first. We've got hydrogen and nitrogen. I'll do hydrogen first just because it's listed first. So we got to put H2 in here. We got to put N2 in here. And I got to raise them to certain powers. You got a 3 in front of the hydrogen. That means I've got to cube the hydrogen one. And I would put nitrogen to the first power, right? So, which doesn't do anything. All right, so that would be the value. That's how we can write equilibrium expressions. Couple things to note here. I'll get myself out of the way. These are all equilibrium concentrations when I'm dealing with Kc. If you have a liquid or a solid in a reaction, so I know these aren't listed with state symbols like S, L, G, A, Q, G. Liquids and solids do not appear in this expression. You don't put them in there. We'll get to an example of that maybe eventually, but you don't write any of those in there, okay? All right, let's see if you can figure some of these out. Looking at question number 1. What would the equilibrium expression be for this? So I recommend that you pause the video right now, see what you get, and then I'll tell you what I get. Did you pause? Because here it comes. Oops, sorry, I hit the wrong button. Bet you didn't see my answer on that one. Let me just go back to what it is. All right, so here it is. Let's move it off to the side. Now, if you got something like this, that the equilibrium expression based on molarities or concentrations is equal to SF6 to the first power over S F2 cubed, all right? So if you're looking at where I got this stuff from, this is a products always go on top. It would be to the first power because there would be like a 1 out front here. And then I put the reactants on the bottom, S to the 1 power and fluorine cubed, right? There's a cube there because there's a 3 in front. Now, if this is what you picked, I would say congratulations if you would have gotten it right, but you got it wrong. Because if you look at this, sulfur is a solid. Gases appear in an expression, but solids do not. The idea here is that if you put a solid like in water sits on top of it, even if the solid is reacting, solids don't take up, they don't dissolve into the water. Okay, that would be aqueous. That's different. Solids sit in a big chunk on the bottom. Their molarity, they don't have a molarity. It's like a chunk that sits on the bottom. Molarity is moles per every liter of solution. There's no solution there. There's solids. So we need to get rid of those. And the right answer is that, but it just takes it out. It actually, it factors into the Kc, whatever that solid would have been. So don't put solids or liquids in equilibrium expressions, please. Okay, second question here. Which chemical expression has the following equilibrium? Now, this is somewhat of a loaded question. We're going to assume that everything in this reaction is all, let's say, gases, or it's all aqueous or something. Okay, if there was a solid or a liquid present, of course, we wouldn't know it based on this. But I can, I suppose I should tell you to pause right now and see if you can get it. Okay, if you didn't pause, too late, here it comes. Well, the reactants are always on top, so the reactants must be SO3. There is a squared here, which means I got to put a 2 in front. I'll put my double arrows. And the products are on bottom. Looks like I've got, I've got O2 to the first power, so that's 1 for a coefficient. And I've got SO2. And it looks like it's 2 of those because I've got 2 here because it's squared, and that would be my answer. And, maybe I could put state symbols or whatever in there, okay? All right, moving on. What about something like this? Equilibrium calculations. All right, so this one would be, just quickly, what is Kc for this reaction? Well, I can write it out. Kc, now again, I'm going to assume here, right, that there's no solids or liquids in here. That's not a good assumption generally, but for this question, just take my word, let's say there's no solids or liquids in here. All right, so this is what Kc is going to equal. It's going to be C D squared all over A B squared. So now I can just plug in numbers and get values. Let me just pause real quick and see what I get. Okay, so I plugged in the numbers here, and if I want to do that, I get Kc is 0.2 times, let's see, what's D? 0.25 squared all over 0.1 times by 0.05, and that's squared. So I get a value of Kc equals 50. And that should be a pretty run-of-the-mill type of question. All right, moving right along here. Oops, forgot I don't have my pen taken off there. Value of Kc, what does that mean when we get different numbers? So you got to look at the number and say, and it'll tell you which side of the reaction has more of it there. Okay, so I'm going to actually go back. Look at the number 1 there, okay? If it says it's greater than 1, reaction's product favoring. If it's less than 1, that means it's reactant favoring. What does that mean? Well, I use this one way in the beginning here as an example, because this reaction was something that was commonly used to make explosives. It was like the first one. It allowed the Germans to go to war in World War I. Otherwise, they had to get their explosives by boat from South America. And that's not really great if you're trying to start a war. So they were able to make it from this. If you look at just the run-of-the-mill reaction here, look at the K. 0.0602. That's much less than 1. That means when you put these two reactants together, hydrogen and nitrogen, it'll make some ammonia, but not a heck of a lot. I mean, look at this, right? Start with 1 molar of each one, and you're getting about, I don't know, see, twice as much. So you're getting about an 8% completion that just stops. You want 100% if you're trying to make explosives, not 8%. That's not very feasible. That's not going to be very good. So we have to test it out. This is one way for us to evaluate a reaction. This number is less than 1. That means whenever we put in it, it's pretty much going to stay mainly on this side. The smaller the number here, the less this thing actually goes to this side, meaning the less of this it'll actually produce before it hits equilibrium and looks like it stops. It's still going, right? But it's not changing anymore. If this is a 0, that means the reaction doesn't work at all. It just stays here. Now, on the other hand, when this gets to be 1, now we're kind of equal. When we get greater than 1, that would be the case where we put these in and most of it converts over to this before it hits equilibrium. if you get a very, very, very large K, let's say like 10,000 or something, that means it's almost like there is no equilibrium. It's almost like it just completely shifts over to the right, and you get almost pretty much nothing of this left over. And in a chemical process, typically you want to make your products. That's the kind of equilibriums you want. So that's what K means. All right, let me shoot back to it here. So 1 is kind of the magic number there. If it's less than 1, that means we're going to, the equilibrium the reaction works a little bit and then it hits equilibrium pretty quickly. We don't get a lot of products produced at equilibrium. If the K is much greater than 1, that reaction is going and you're going to get a lot more products. Okay, so if we're looking at this and it says, okay, here's some Kc values, which one would they be? Well, this is less than 1, so it's reactant favoring. Greater than 1 product. Ooh, this one's really product favoring. And less than 1, that's very reactant favoring. You don't get much of anything at all on that last one. Okay. So is this reactant or product favoring? I'm not going to go through this. I'll let you pause and get the answer, and then I'll just tell you what my answer is here in a second. Alright, so this was the same question as I did before, and we got that Kc was 50. So that means this is product favoring. So if you put all these things in there, what's going to happen is these two numbers will go up, and then before they hit equilibrium, and these two numbers are going to go down before it hits equilibrium. That's really what that means. So you can kind of predict which way things are going to go. Alright, here we go. Here's some last ones here, some calculations, and I put medium. We'll get to the hard ones some other day, okay? Well, here we go. We've got this flask, 2-liter flask, and we put into it at equilibrium, we find in the 2-liter flask there's 0.22 moles of water and 0.038 moles of hydrogen. We know the equilibrium constant on this one. First question is, what is the concentration of O2? Second question is, what are the units on Kc? And the last one is, what is the value of Kc for the reaction? Alright, so let's try some of those. First things first, let me just sort of move that up into the corner there. What is the concentration of O2? Well, let's get the concentrations of water. Molarity, so the concentration of H2O, not H2N, equals 0.22 moles over 2 liters, which is going to equal 0.11 molar. And then let's figure out what is H2 at equilibrium. It is going to be 0.038 moles. Well, you can hardly even read that. 38 moles per every 2 liters. And that's going to be 0.019 molar. So we could actually plug this in and solve. So I know that Kc, which is 2.4 times 10 to the minus 3, equals... Now let's see, we got to have oxygen on top, so that's there. Don't know it. It's raised to the first power. Hydrogen's value, 0.019. Hydrogen has a 2 out front up there, so that should be squared. And water's got to be on the bottom. That's 0.11. And that also has a 2 out front, so that's also squared. So let me pause real quick, type this in my calculator, and solve for O2. Okay, so when I plug this into my calculator, I'm getting that O2 at equilibrium is going to be approximately equal to about 0.08 molar for that first question right here. Okay, so that's the first one. The second one says, well, what are the units on Kc? All right, so this has nothing to do with numbers. This is just like, what would they be? So let me switch inks for that question, the second one. Okay, so I'm going to switch inks here. Well, let's take a look. Kc, I'm just going to write it out. Kc equals, it was H2 squared O2. I guess I'm writing it backwards from the one above it, but that hopefully doesn't throw you off too much, over H2O squared. Alright, so with that being the expression, why don't I plug in molarity, because that's what they are. And that's how I can figure out what the constants are. So, if I plug in M for H2, that's squared, I'll plug in an M for O2. Now let's plug an M in for molarity for water, M squared. Alright, so if I want to know what the units of Kc are, well, I got an M squared on top and an M squared on bottom. That means the units on, this number up here is just molarity, right? So it's going to be just molarity. You can get really goofy units. I'm not a big fan of these kinds of questions because these questions tend to just be sort of gotcha things on tests. but I'm going to throw them at you because you're going to see them on the AP and IB exam. They really have no bearing whatsoever on anything that anyone really uses in real life, but unfortunately we got to be able to see how to do them. Okay, the last question. This is a really, really good one because this one I know gets asked a lot as well, but it also does have some practical abilities. What about this? What would we do for the reaction there? And you know what? On an AP exam, IB exam, a lot of times they're not necessarily looking for the values, the numbers. I'll show you how to do that. They look maybe like non-number based. Okay, so let's take a look. What is the difference between the one I highlighted in blue there and the one here I'm going to highlight in yellow, the original one? So to me, it looks like two things here. Number one, the reaction is flipped. Oops, I don't want yellow. The reaction is flipped. You know, like it's been reversed. All right, so water was it was a reactant, now it's a product. The other thing it looks like is like they divided everything by 2 here, right? Okay, so what do we have to do then to make this stuff match? Just real quickly, what I'm going to tell you is that when you flip a reaction like this, like you just sort of switch it around, that means you're going to take the Kc and then you're going to like make the denominator the numerator and the numerator the denominator. And then when you divide the coefficients by 2, well, that's taking the square root of something. Now, if that can be a little confusing for you, here's another way you can look at it and say, all right, well, what I'm going to do, this is the Kc, the original one. Let me draw the Kc of the new one here. So let me just make this a little bit smaller. Okay, so the Kc of the new one is going to be, and I'll put new, Kc new, I guess. It's going to look like this, H2O over H2, and then it's going to be O2 to the 1/2 power. So you've got to think, okay, what do I have to do to this one, the original one, to turn this mathematical expression into this one? Well, right now it looks like I have to flip it. So flipping it means that I am going to do 1 over Kc. But if I just flip it, you know, then I'm still going to have these squareds here, that square there on the bottom. I don't want that. I want those squareds gone. In fact, I want this to the 1/2 power. Well, how do you change a 2 power into a 1 power? You square root it, okay? So then I can add that on here. And I don't know if you want to put square root of the whole thing. I mean, they probably would do it like this. So typically, this is where the AP and IB question would stop. But if you really wanted to know the numerical value, I would hope at this point it would be fairly simple for you. You have the numerical value of the original Kc, you know, so you could plug it in there and, you know, 1 over the square root of that. And that would be equal to the value of the new equilibrium constant for that reaction I've highlighted in blue. Okay, that's something you really want to make sure you can understand, because I guarantee you're going to see that concept again. So there you go. There's your start to what equilibrium is, and some of the, you know, the reaction constants, what the reaction constant means, and a little bit of sort of finicking it around, you know, sort of like playing around, flipping it, square rooting it. If we aren't, I should maybe add one more thing here in just a second, but that's kind of the gist of it. Let me just add one more thing I just thought of real quick, though. Let's say I did this. I want to do a new equation here. Let's say instead of me doing it with a 2H2O, that's what Kc is. Instead, I want to do it all by 2, right? 4H2O in equilibrium with 4H2 plus 2O2. Let's say that's what the one is, and I want to know what's the Kc expression now, right? So I just took the original one and multiplied everything by 2. All right, so again, maybe you're thinking, okay, well, I get it. That means I'll just square everything. So hopefully you got that. But what would this look like? So now my Kcn new would be H2 to the 4th power, O2 squared over H2O to the 4th power. How do I turn that expression you see for the original one into this? Hopefully you can see if you square everything, it'll turn into that. So what does the Kc over here, the new Kc, look like? Well, it's the original one, but just squared. All right, there you go. That's it. I'm done for today. You've got enough to digest on day 1. And I wish you luck.